Okay, well, we'll make a start. So, first of all, welcome everybody. So, those are here in the room, okay, and those that are joining us online. This is also being broadcast as a webinar as well. So, we have a whole audience online in addition to those that are here today. So welcome to both audiences. My name is Steve Lyons. I'm a lecturer here at the university, but the role of this evening tonight, I'm also a science theme lead in the Geological Society in climate and ecology. Okay? And it's in that capacity that we're putting together something slightly different. We've never tried this before as a science theme, let's call it a rail show rather than a road show, around the UK, and hosting a series of talks related to both climate and or ecology around the country, culminating in a conference that will be held at the John Stock at Burlington House in the summer of 2025. Okay. And we're starting off in Plymouth, so this officially is the launch event for this series. Okay, and
Glad you've got the problem. I think it's if you don't do anything for 5 minutes, it sort of loses it. I think you have to go in and out, maybe.
Yeah, we've lost the green outline of the screen, which would suggest that we may not be sharing anymore. So it's always good to get the issue sorted out of the launch event, rather than the throughout the series.
Oh my God, we got kicked out of Zoom, didn't we?
We've been kicked out of it. Okay. Can the media still see us online? Yeah. Okay, so can you still see the slides online?
No.
Back online. Okay. So yes, we're starting off. So this is the launch event. We're starting off here in Plymouth, and then we'll proceed in Aberystwyth, Liverpool, Glasgow, Durham, Birmingham, then final ending in London, as I said, in Burlington House. So, with that said, it's my pleasure to introduce Professor Erd, who's going to be giving the first talk in this series. Erd has been here the same amount of time I have, so over 20 years. He's Professor of, majority of you probably know, Professor of Coastal Geomorphology, and he's going to be talking today about the impact of sea level rise on atoll islands is drowning the inevitable out. Okay.
Thank you, Steve. I think I'm unmuted, so that's good. Have you unmuted me?
Muted.
You've unmuted me, right? Very good. Thank you, Steve, and thanks to the Geological Society for inviting me, a physical geographer, to open this this tour of the UK, talking about climate change being, I guess, off the rails and the implications of that. The subject of my talk, the title of my talk, is the impact of sea level rise on atoll islands. Specifically, I want to address the question, is drowning the inevitable outcome? Now, I can go two ways now. I can either give you the answer now, at the risk of some of you walking out because you've got the take-home message, or I can actually let you leave the tension, leave you on tenterhooks, and give you the answer at the end. I'm going to do the former. I'm going to tell you the answer to this question now, because I feel that is the key message of my presentation, is the answer to that question. But before I do that, I would like to take a little bit of time for you, as the audience, a little bit of audience participation. I'm not Jimmy Carr. I'm not going to single anyone out, except maybe perhaps you, sir, with the green shirt. Pretend you're the audience, pretend you're the general public, and you get your information from the media. What do you think the answer to this question is from a general public point of view? Not your personal view, but from a general public point of view. So I don't want anyone on the fence. So it's either yes or no. So from a general public point of view, who thinks that drowning is the inevitable outcome? Okay, so I assume the others don't. Okay, then now I'm going to sort of bet maybe 60%. So now, from your professional point of view, you may have studied this phenomenon before. You may have read papers on this. You may have maybe have different ideas about it, or maybe you think like the general public. So again, show of hands, who thinks from their professional point of view that the answer to this question, is it drowning the inevitable outcome? Who thinks it is yes from a professional point of view? Okay, a lot less. So that is good. I feel a little bit like I'm preaching to the converted, but there's a couple of people who think yes from a professional point of view. So that's great. So the answer to that question, I believe, is actually no. I don't think it's the inevitable outcome. And I believe that atoll islands have the natural ability to potentially prevent drowning from happening by keeping up with rising sea level. That is my view. And I will use the rest of this talk to use geological and geomorphological field evidence, physical modeling results and physical experiments, as well as numerical modeling to make the case, and hopefully I can sway a few of your opinions. So I believe that as atoll islands are being increasingly flooded, that in addition to the water that goes on the top of the island, the waves that wash on top of the island also bring sediments to the island. And I think if successive flooding events or overwash events have the potential to raise the level of the island, very much like a salt marsh. Now, this presents an interesting challenge for the communities that live there, because what I feel, what is partly their savior, the flooding, is at the same time posing a threat to those coastal communities. Well, I'm a physical scientist. I don't really deal with the application of it for local island communities. But I think my role is providing the knowledge, the understanding, the tools to understand this natural ability for islands to adjust. And then hopefully that will then be taken into account in sort of sociological, socio-economic adaptations. So that's where I'm sort of coming from. Now, before I start, I do want to make crystal clear what I mean with atoll islands. I did on ChatGPT this morning, I asked, what are atoll islands? And it came up with a perfect definition of coral atolls. And we see here on the top left, an atoll, one of the Maldivian atolls. Atolls are the sort of geological foundation of the islands that I'm going to be talking about. These atolls are 40, 50 million years old in the Maldives. They're recording multiple sea level rises and falls, slowly subsidence. They are actually underwater for most of the tidal cycle. They're not islands as such. But I'm talking about the deposits of sandy and gravel carbonate sediments that sit on the rim of these atolls and sometimes also in the lagoon itself. Those are the islands I'm going to talk about. So it's not about the coral reef structure. It is about the loose sediments that sit on top of the reef structure. So I want to start with some context. This is nothing new to anyone, but it's important to sort of lay out the stall here that we know sea level is rising and it's going to be increasingly happening at an increased rate. We have the IPCC bringing out various predictions, and there's lots of uncertainty in the models. There's uncertainty about emission scenarios. So you get all these different types of curves. But the take-home message of this is really that there will definitely be a rise in sea level between 40 and 80 centimeters by 2100, possibly a meter. Some people think even more. So it's important to have that sort of number in mind when we start looking at the elevation of the islands above present level. There's also talk about climate change resulting in a change in storminess and changes in the wave climate. And the plot actually shows the distribution of very extreme wave heights, 1 in 20-year wave heights across the globe. The red lines are the atoll lines are actually between the red horizontal lines. The Maldives is the red square. And immediately it shows that actually the tropics, which are the atoll islands occur, are actually quite low energy environments. Actually the lowest in the world. So low energy conditions generally, but occasionally tropical storms can occur, but they do not occur in a narrowband right across the equator, where most of the atoll islands are. So relatively calm conditions compared to the rest of the globe. The plot left shows the changes in these extreme wave conditions that are expected as a result of climate change. And the units are like the change in meters over the next 100 years, between 1 and 2 meters in the roaring 40s here. But the equatorial sort of region and the Maldives and the Pacific, actually there's not clear evidence of an increase in storminess. Now, this is actually not that important, that extreme wave conditions are not necessarily expected to increase significantly because of the rising sea level, the impact of the storms will increase anyway. So even with the same storm conditions, a rising sea level will increase the impact of storms. And this is illustrated in this slide. They use a very unfortunate sort of name, historical centennial events. This is basically the 1 in 100-year water level event, a very extreme water level event. And if you look at where that level is, anywhere on the coast, it's obviously higher than the once in a 10-year event, which is above the once in a year event, which is higher than the once in a month event. And what this plot sort of conceptually shows that what is now a 1 in 100-year event, at some point in the future with a rising sea level, may become an annual event. And the interesting thing is, if you plot when that is going to happen, when does a centennial event becomes an annual event, it's indicated by these colors. And the bottom line is, the message really is that around the equator, where the atoll islands occur, these centennial events are likely to occur on an annual basis by 2040, 50, 60. And this is because these equatorial regions have relatively low storm surges and relatively small tides. So a 1 meter sea level rise has a huge impact on these sea level effects. So in order to sort of illustrate what the effect of that higher sea level together with maybe storm conditions is, I just have 2 slides to show a little bit about what the typical atoll island topography is, and then I'm going to show a slide on the typical processes. So this is a nice schematic diagram, and several key features are a fore reef, a very steep fore reef that goes very, very deep where most of the waves will be breaking. Then you have a reef platform, which tend to be often hundreds of meters wide, that are very close to mean sea level, often dry at low tide level. And then you have the island. And often the situation repeats on the lagoon side, but we're going to be focusing on the ocean side. So a reef platform that has always very shallow water depths because it's very high in the tidal frame, and an island that is extremely low if you compare it with sea level. So a typical island here in the Maldives, we have the high tide limit here. The actually elevation of the island is only 1 meter above spring high tide level. So you say you don't need an awful lot of sea level rise to allow the flooding of that. You probably don't need an awful lot of wave action maybe also to flood that. So we also have to look at the processes, the wave processes. And if I look at the processes associated with that morphology, already mentioned, the waves are approaching the reef edge and break. They lose most of their energy by the time they reach the platform, the shallow water of the platform. So they break, and as they break, they dissipate their energy. They lose their energy. The energy is lost by breaking. But 2 interesting things happen at the same time. So while the ocean waves dissipate and lose their energy and decrease in height, the water level across the reef platform is elevated. It's almost like the breaking wave provides a force on the water surface that elevates the water on the reef platform. So the water on the reef platform is higher than that of the ocean. I'll show you an example of that in a minute. And the other thing that happens is the waves that are breaking on the reef edge, they vary in size. So you have groups of large waves, groups of small waves, groups of large waves, groups of small waves. That causes almost like a breathing of the water level on the reef platform. We call that infragravity waves or far infragravity waves or very low frequency motion. I'm calling them long waves. They're really long minute fluctuations of the water level that's associated with the wave groups pounding on the fore reef. So it's illustrated, and then the key point is then if the ocean waves, the tide level, the sea level, the wave setup, and these long waves, if they cause a wave run-up that exceeds the elevation of the island, then the island will flood, and then you get overwash and island flooding. So this is showing some data that we measured across an existing reef in the Maldives, so offshore, and then these are the 4 locations where we measured the ocean wave height, and we see big waves breaking, immediately a loss in wave energy, a very small ocean waves on the platform. That is the dissipation. Similarly, if you look at the mean water level on the reef, the mean water level in the ocean is 0, so that's the mean sea level. and we see that the water level is elevated across the reef. And the bigger the waves, the red dots, the higher the wave setup. Roughly, wave setup is between 10 and 20% of the wave height. And what that means is that with a 5-meter wave pounding on the reef, you can have up to 1 meter of setup, elevating the water level. And then these long period waves that are also generated by the wave groups, well, they're also very small outside the reef system where the waves are breaking, but they are also quite substantial on the reef itself. And again, they get bigger as the waves pounding the reef get bigger. And again, we're looking at 10 to 20% of the height of the waves of that really low frequency motion is 10 to 20% of the wave height. So 5-meter waves, we have maybe 1 meter setup, and then we have the water motion going up and down by about 1 meter. So the ocean waves, the wave setup, and the long waves together result in wave run-up. And when the run-up exceeds the elevation of the island crest, the island will flood. So current situation, we have an island here, we have large waves here breaking, very small waves, small run-up. Normally, the run-up is rarely exceeding the elevation of the island. So most islands do not get regularly flooded at all at the moment. And the freshwater lens that is present on most islands remains fresh. Whereas if we increase the sea level, we're getting bigger waves breaking, we're getting increased water depths across the reef platform. We still have our setup, we still have our long period waves, the breathing of the reef platform water level, and our run-up can exceed the elevation of the island, and we get island flooding or overwash. And we get contamination of the freshwater lens by salt water, and that can take months to clean out again. So this is assuming that the island remains exactly the same. So the notion of a stationary island is really critical here. We're changing the waves, we're changing the water level, but we're keeping the water level, we're keeping the island the same. And this is what I'm contesting. But anyway, if you do that, and we look at some previous research, you get the very widely publicized messages like, most atolls will be uninhabitable by the mid-21st century because the rising sea level will increase the water level across the reef and will increase the run-up and will increase the flooding frequency. Too much flooding happening, the freshwater table gets contaminated and people can no longer live on the island. This is the common view, and this is why probably most people put their hand up in the beginning, because that's what the media emphasizes. But there's other views as well, based on, and I just have to make the point here, this is based on numerical modeling studies of waves and tides and currents and sea level, but with an island that remains the same, hydrodynamic models. But the island doesn't stay the same. Islands change over time. And here's another paper based on satellite data, satellite-derived shorelines. People have been mapping shorelines. Satellite data is available since 1980, so you can look at 40 years of shoreline data. If they're all drowning, then we've had about 1 foot of sea level rise since the 1980s almost. So the islands should shrink. But in fact, quite a lot of the islands are actually expanding and not shrinking. So evidence from the shoreline data suggests that a lot of islands are actually getting bigger and not sinking. It's nice to see the media headlights that you get. This is quite a nuanced paper. They're very nuanced. That's the headline. Similarly, this one, geological data, dating of islands, and finding out that most of the islands are actually, a lot of the islands have formed and developed under the influence of rising sea level and stormy conditions. And in fact, atoll islands are actually storm deposits. So what they're saying, well, if we get a rising sea level and maybe also increased storminess, well, maybe there's going to be a reactivation of the island formation. So again, quite nuanced, coral reef island initiation and development under higher than present sea levels. The headline is climate change could actually help coral islands rise again, but they're still at risk. Our view is, again, I think a bit more nuanced. Coral reef islands can accrete vertically in response to sea level rise as a result of this overwash process. A brighter future for coral reef islands, again, fairly nuanced, AGU. So I feel I need to talk a bit more about this overwash process because it's key to this island natural adaptation. Okay, so what we're seeing in the bottom right is actually a simulation, a numerical model, a hydrodynamic model that brings in the waves from the seaward side and breaks them on the reef edge, propagates them across the reef platform, and then actually you can see them running over the island. So we get overwash here. Island's not changing here. You can actually see the wave going down the slope and then going into the lagoon. The top right are observations. I think these are observations after a tsunami, which is also like a major overwash event. And we can see like 20, 30 centimeters of fresh sand being deposited at the edge of the shoreline by an overwash event. And we can see that deposit can extend 10, 20, 30 meters landward. Obviously depends on the situation, but we can basically see overwash results in deposition of sand and an elevation increase of the island. And it occurs under conditions of extreme wave conditions, large waves, and probably a spring high tide. And it moves, the waves that wash over the island take the sand and the gravel from the platform or from the front of the island, the beach, and basically drop it on top of the beach, on top of the island. And that in itself raises the elevation of the island. That is the principal process that I'm going to talk about. Overwash raises the elevation of the island, and therefore is the natural ability of the island to keep up with rising sea level. The question, of course, is how much does the deposition happen, and how does that compare with the amount of sea level rise? That's a different thing. And this is a real overwash event on one of the Maldivian islands we studied. And I just want to make the point that these are not necessarily very, very dangerous catastrophic conditions. We see the waves washing onto the island. These are the little ones, and these are more coming in a minute. And I'll show you some evidence of this event in a minute as well. So these are 10, 20, 30 centimeter big waves that are mainly a result of this breathing. So not much happens, and all of a sudden this surge of water comes, and then the water retreats again, and then you might have another surge. And it only happens for a couple of hours around high tide, and at low tide it's all calm again. And you can see the flooding, you see the sediment being moved. That is an overwash event. This was the biggest overwash event that happened on this particular island in the last 10 years. In fact, it was the biggest event since the 2004 tsunami on this particular island. So a very rare event, did all the right things and didn't really have any catastrophic damage. And this is what many of the islands looked like after this particular event. We did a post-storm survey, and universally, depending on where you were, there were deposits in amongst the mangrove forest, there's sand sheets amongst the palm trees, again, lots of gravel sheets, 20, 30, 40 meters wide. Also gravel on the roads, so the overwash actually extended into the village and deposited a couple of centimeters of gravel on the roads there. Little holes in the island ridge were cut, and that was another conduit for water and sediments. And we also saw a lot of sediments being stripped off the lower part of the beach and the formation of these very coarse gravel ridges. Again, a depositional process that raises the elevation of the island. Okay, so how do we measure this? How do we collect data on this process, which is very rare, very unusual, and can be quite damaging? But main issue is you never know where it's going to strike. So if you want to monitor that particular process, you probably got to put your instruments out on 100 beaches in 100 islands in the Pacific and the Maldives, in the hope that over the duration of your research project, you'll actually catch one of these events. I mean, it's virtually impossible. So what we did, our approach has been to do physical modeling. So basically build a replica of an atoll island and a reef in a flume, and then do experiments. Now we started in the coast facility here, and we did a 1 in 50 scale experiment, which means everything is shrunk down by a size of 50. So rather than the island being 2 meters high, need to do a quick sum, the island was only 8 centimeters high. So rather than have 5 meter waves, we have 10 centimeter waves. And everything was scaled down to a 1 in 50 scale. So it's a tiny beach. This is the real size of the flume. It's about 20 meters. Tiny island, about this high, with a reef platform made out of plywood. So a very simplistic representation of actually a real reef island with a platform. And then we just basically filled it with water. We turned the wave paddle on, generating waves, and then we slowly increased the sea level. We replicated the 1 meter sea level rise, which was actually a 2 centimeter sea level rise. And this plot here shows how the island changed. So we started off with a black line, double-ridged atoll island based on a real island, but shrunk down on a 50 scale. I've actually multiplied the dimensions of this lab experiment by 50, so it looks like a real island. And over this 1 meter sea level rise from here to there, the island retreated, but at the same time, it built up its crest. So it moved back 40 meters and it raised its crest by almost 70 centimeters. So it's not a meter, but clearly it was responding to a rising sea level. It wasn't simply drowning. And bearing in mind, this is a very small scale experiment in a flume. We repeated this in the wave basin. So now we have a small swimming pool, 10 by 20 meters. We built a plywood short platform, which was the reef platform. And then we built this sort of funny shaped atoll island on top of it. The same sand, the same dimensions. We did the same thing, different wave conditions, different rates of sea level rise. And then we basically mapped the evolution of the island using a scanner. And these are the sort of the end results. So the starting point is this is the island. The dark blue is the island, but actually then this is the platform. And then we go from left to right, we go to a rising sea level from 0 to 1 meter. And we can see that the island shrinks, but the color of the blue increases in intensity, which basically means the sand gets concentrated more. At the same time, the island builds up. And if you go from top to bottom, we actually have a 1 meter wave, a 2 meter wave, a 3 meter wave, and a 4 meter wave. But if we push the system hard enough with really big waves, we can actually destroy the island as well. So it's not just like every island will just simply adjust to rising sea level and keep up. There are some conditions attached to it. But the key really is that the island adapts itself or tries to adapt itself to rising sea level and doesn't simply drown as if it's made out of concrete. Now we scaled this up. I just got back from the Delta flume in the Netherlands, where we repeated some of these experiments over a 3-month period. We rebuilt another reef platform with an island, but now on a 1 in 3 scale. So that basically means that rather than sending 4.5 meter waves down, we sent 1.5 meter waves down. So really big waves we sent down. Rather than a 1 meter sea level rise, we had a 33 centimeter sea level rise. But it's a big facility. We're looking at almost 300 meter long. This is the island. We're just doing some survey work here. That blue thing is called the wave paddle. It basically moves backwards and forwards and generates realistic waves anywhere between 0.5 meter and 1.5 meters, sometimes even bigger. These waves approach the reef platform. That's where they break, very loud thumps when the waves are really big. When a big group of waves arrives, then they propagate across the reef platform, and then they either reach the crest of the island and overwash, or they just swash up and down here. And all the sort of little symbols are instruments to measure the water level, the waves, the currents, and those sorts of things. So there's the wave paddle, sends a big set of waves down. It probably breaks here, and this is across the platform, and it's just this wave will just hit the bottom of the beach. I'm going to show you one of the runs, and the island is here. This is the crest of the island where these instruments are, and we can clearly see that the waves are actually overtopping, overwashing over the island. We can see that the water is brown. The water is brown because it suspends the sediment at the front of the island. So as the waves wash over, they'll take the sediment from the front of the island and move it towards the back of the island. I'm going to swing to the right, and you can sort of see the overwashes extend across the whole of the island, and then they go into this sort of artificial lagoon. So what we're really looking at is what does that do in terms of raising the elevation of the island? And like I said, we've just got back last month, a couple of weeks ago. I'm going to show you 2 results, just hot off the press. So we have in blue, we have the original island. This is the dark blue here. And every sort of set of symbols shows 1 hour of wave conditions with the sea level rising at about 1 centimeter per hour. So this is like a 34 centimeter sea level rise, which is the equivalent of 100 years of sea level rise. And we're just sending these waves down. And what we can see is the same as we saw in the small scale test. The island is receding, but at the same time, the island is also building up. Now, there's a couple of things to mention here. One is obviously the island will get narrower. And there's no other way of raising the crest of the island and the island other than narrowing the island, because you have a finite amount of sediment. And the other thing too, so the sand required for raising the elevation, the waves source from the front of the island. So the island will shrink, no doubt. And the other thing to mention is that actually the amount of accretion is actually a bit smaller than the amount of sea level rise. So you could say, well, maybe this island is slowly losing it. It's not really keeping up with rising sea level. But we've done a whole bunch of different tests with different rates of sea level rise and different wave conditions. We could say, well, maybe this one's not keeping up and slowly losing it. But if you have a village on the island here, and you want to sort of assess whether the flooding regime is getting worse or is just about that you can live with it, what is more interesting is to actually look at how much water over these hours actually goes across the crest and floods the island. So we've been measuring what's called the overwash discharge, how much water is going over the crest and onto the island. If the island is losing it, that overwash discharge should increase in time. It should get more, the flooding should increase in magnitude and should increase in frequency. If the island keeps up with rising sea level, the amount of water should remain more or less the same. So again, this is just almost hot off the press. These different colors indicate different wave conditions that we expose the island to. And every wave condition is 1 hour, and then we raise the sea level by 1 centimeter, we have a different wave condition. We pick from this spectrum of wave conditions where C1 is a very moderate storm, and C6, the dark blue one, is a very intense storm. So we have this variation in wave conditions. What this basically shows here on the x-axis, on the y-axis, is the amount of water that's flowing over the island, the mean overwash discharge. Now, to put this into context, anything 1, 2, or 3 is nuisance flooding. It's annoying. You get wet, but certainly no danger to people. Anything sort of between 5, 10, 15 is, damaging houses potentially, but still quite modest overwash discharges. It's not going to move cars. You really have to go to 25, 30, 40, 50 for that to be alarm. So the overwash conditions are relatively benign. Not saying that they're nothing to worry about. And particularly C1 and C2 and C3, well, they are nuisance flooding, but they nevertheless build up the island. And then C5 and C6, which are really extreme storms, well, even they have an overwash discharge that is relatively modest. But the most important thing here is that actually, if you look at the dark blue ones, I don't see a dramatic increase in the amount of overwash discharge. I don't see anything in the data here that the island is losing it, because the amount of discharge for any of the similar colored runs is very similar. So I would say the island is probably keeping it more or less up with rising sea level in terms of how it behaves and in terms of the flood frequency. So the island retreats and builds up, but less than sea level rise. However, the amount of water over the crest does not increase dramatically. So I think the flooding regime is fairly constant, even though the island is maybe, in an elevation sense, seem to be losing it a little bit. So the next step then is to do numerical modeling. Well, numerical modeling is a lot cheaper than physical modeling. The delta flume experiment costs 800,000 euros. It's very expensive. And once you do it, you can't repeat it. With numerical modeling, you can repeat, you can turn the computer on, you change the island shape, you change the wave conditions, you run it again. We use the model called XBeach. I just don't really want to go through that list, but the idea is it's probably the most realistic process-based model that includes the waves and water level and groundwater and wave setup and long waves and sediment transport, morphology, everything that it should include at not an incredible cost in terms of computational requirements. So the most important thing before you use a computer model or a numerical model for this sort of thing, you need to make sure that it's doing the right thing. So you do your model calibration and your validation. And I'm just showing you a comparison between the measurements in the flume, in the physical lab, and the model results. So in terms of the dissipation of the waves from here all the way down to the island, the waves break and shoal, and then they reduce in height. The model seems to be a very good job in reproducing that. The model is the line, the measurements are the dots. In terms of the long wave height, well, again, fairly good correspondence between the two. And in terms of mean sea level, we also see a very good correspondence. So we have some confidence in the model. The model's supposed to be doing this right. The more challenging thing is, can it reproduce how the island responds to rising sea level? Again, it does a pretty good job. The dashed line is the start. Then we're raising the sea level by 0.5 meter. The bubbles are the observations in the flume. And those gray lines and the black line is the numerical model. Now, we're not really reproducing this very well. There's a bit more sand at the lower end of the beach in the model and a little bit less washover, but the amount of retreat and the amount of increase in elevation, again, is pretty good. So we're pretty happy with that sort of performance. Not only is that being reproduced, also the rate of building up the crest, the rate of the amount of retreat is all pretty good as well. So it's sort of slows down a bit, and the model seems to be doing that as well. Now, the real beauty of the model is that you can make measurements in the model results that tell you about the process. So, for example, we want to know how much water is going over the crest. What's the overwash discharge, and how does that help explain the behavior? Virtually impossible to measure in the field, very difficult to measure in the lab, but you can basically just pull a model grid node out of the model, and you can actually calculate this. And what the amount of water that goes over the crest during this particular run, again, we're looking at this time series of overwash discharge, is well below this critical value of around 10 liters per meter per second. Again, this is, again, still nuisance flooding. The key point is nuisance flooding is already sufficient potentially to elevate the island. We don't need catastrophic overwash to do this. So the full-scale numerical model reproduces the small-scale physical model very well, and our next step really is to use the 1 in 3 model results that we did over the summer to do a bit of a more model validation calibration. Now, the one problem with the model is it still takes a long time to simulate. It's a process-based model. It measures the waves going up and down. It just makes calculations every second or even faster. And if you want to do a 100-year simulation of a rising sea level, you want to know what the island will look like by 2100. That's an awful lot of calculation time. And in fact, it's almost one-on-one. So it would take almost 100 years on the PC to calculate. So we need to do some tricks. I'm just going to talk you through the tricks without, just for those who are really interested in it. We take 40 years of wave data from the local site. We statistically analyze that wave data set by extracting all the storms from that data set. Height, the duration, the direction, the period, and we struck all that in a statistical method. We calculate all sorts of statistics with it. And then from those statistics, we then generate a 100-year time series of wave conditions. So we would probably include in the 100-year time series storm waves that are not actually measured in a 40-year time series. So we create a synthetic time series of storm conditions. Compared to all the wave conditions, we're already achieving a 90% reduction in the wave conditions. We're not looking at the conditions that are not storm conditions. We're not interested in it. We're only looking at the storms. Then the second thing we do, we look at all these storms, we combine them with the water level changes, the rising and the falling tide, and over a long simulation, we slowly have the sea level rise in there as well. And we interrogate that data set, and again, using machine learning to identify those combinations of wave height and storm conditions and water level that we think will reach the crest of the island and result in overtopping. All the other storm conditions that happen at low tide, we don't look at. Storm conditions about very short periods, we're not going to reach the crest, we don't look at. So we achieve another 85% reduction in wave conditions. So from this 100-year time series of hourly wave and water level conditions, we end up with a subset of conditions that are manageable. They're only the red dots here in this particular case. So we go from 10,000 hours of wave and water level conditions to a couple of hundred of the most extreme conditions, and we can model them over a 2, 3, 4 week period. So what I'm showing you here is one of these 100-year simulations. This is the wave height. That's the wave period. This is the position. Sorry, this is the discharge, overwash discharge across the crest. This is the elevation of the crest, and this is the position of the crest. So we have a whole range of different wave and water level conditions that do different things. Some wave conditions lower the crest, but overall the crest is increasing. Most of the conditions have less than 5 liters per nuisance flooding. There's one particular event that will show up as being a very extreme event that could potentially be quite damaging, but after that the island recovers again. So here we now have almost like a tool to start exploring the relationship between wave, water level, and island adjustment that we can use to do other things with. Now, one thing we did is to look at adaptation measures. We looked at what happens if we do things like, what happens if we do things like having an artificial sort of reef restoration on the reef platform, take a bit of energy out of the waves. A lot of people thinking that's a good idea. What is the effect of a degraded coral reef, where all the coral dies and the roughness of the reef edges is much less, so it's much smoother, there's less dissipation? And how does that compare to if we don't do anything at all? And there's really not really that much difference, but all in all, whatever we do, we always result in retreat of the island and a increase of the elevation of the crest by the same amount as the amount of sea level rise. Coral degradation leads to higher crests because the waves are going to be bigger by the time they reach the island, but also more retreat. Reef reconstruction or introducing roughness structures, we still see the same thing, but less retreat and less high elevation of the crest. So again, we can start testing the efficiency of different adaptation measures, and then we can also start looking at what is the effect of that on the flood frequency and the flood magnitude, and that may have then a bearing on whether the island might still be inhabitable or not, whether people can deal with that. Now, there is a big elephant in the room, that's the sediment supply. I can see some of you thinking, what about sediment supply? Do you need sediments to keep up with the rising sea level? And what about if the coral reef dies and there's no more sediment coming into the system? It's a really important question, and we need to be able to put a finger on it in terms of quantifying that contribution. All the results I've shown you is assuming that there's no sediment coming into the system from the reef, the living reef system. So no sediment is coming from the reef platform and no sediment is coming from the forereef, just a close sediment amount. So what about the sediment supply? And if we look at geologically at Atoll Islands, well, actually, if we look at Atoll Islands, there's tons of sediment. There's loads of sediment everywhere. Sand, gravel, silt, cobbles, everything. All that sort of stuff at some point was living, and at some point was not part of the island. And at some time, it would have been thrown onto the reef platform to form an island. And actually, geologically, 6,000 years ago, 7,000 years ago, maybe, there were no islands. And these islands started developing when sea level sort of more or less stabilized. Some islands formed with a continuous rising, some with a constant sea level, and some with a falling sea level. But nevertheless, the sediments that actually end up on the island would have been derived from the reef system. And we need to we need to quantify that to understand how much of that sediment is actually coming. So large amounts of reef-derived carbon sediments are required to atoll islands to maintain them and generate them, but how much? And just to look at some of the sources, most of the cobbles, most of the coarse material is just coral that get ripped off during storms and then gets chucked onto the platform and then maybe ends up forming a rubble island or a rubble ridge. The sand has a number of sources. I find this the most interesting one. I was flabbergasted when I found this island 5 years ago. Maybe some of you already know. Most of the sediment that sandy atoll islands are made from have gone through the intestinal tract of the parrotfish. That basically they're gnawing on the live and dead coral. They take the lichen, the bacteria, and the polyps, and then they secrete the sand. The bigger the parrotfish, the bigger the beak, the bigger the lumps of gravel that come out the other end. So anyone planning a honeymoon to the Maldives, you're walking around, you're picking up that white sand, well, it's gone through the parrotfish, likely, at least some of it has. So that's where it comes from. And what happens if you add sediment to a simulation? We did this in the flume as well. So this is two examples of rising sea level go from black to red with 3-meter waves, from black to red with 4-meter waves. And then we add sediment. We just add a certain amount of sediment to the simulation. And actually, we see that the 3-meter wave simulation, all of a sudden, we're not retreating the coast at all. We're just building the island up without shore retreat. The 4-meter one that almost completely destroys the island, still not great, but the retreat is a lot less. So, of course, adding sediment to this process is going to slow down the retreat, but it's not going to necessarily enhance the increase in elevation. The increase in elevation is purely the result of hydrodynamic processes. Now, the amount we added here, there's some numbers there, I just have to believe me, was a lot, way too much. So we added a lot of sediment to generate that significant difference between with and without sediment supply. So it feels like a lot. So we need to know a bit better this number. So what we've done is a very new study. We looked at all the Atoll Island studies that had good data on dimensions of the island, topography of the island, and most importantly, some chronostratigraphy of the island, some dates of when the island formed and how far it's formed. And if you know the volume of sediment on the island, and you have some sort of time window over which this developed, you have the volume of the island, you divide it by the number of years, then you divide it by the sort of the circumference of the island, and you get a sediment supply. So you get an average delivery rate, in this case per unit shoreline length, you get a number. Now, those numbers may not mean much to you, but I'll tell you in a minute what they do. So we had 29 islands, huge variety in ages of these islands. Some of them are very recent, like Jin in Marshall Islands, and some of them are quite old, and some of them formed over 5,000 years, and some formed over a relatively short period of time. Anyway, we got an age. Overall, the sediment thickness is around 2 meters. The surface area, anywhere between 10 and 100 hectares on average. The length, about 1.2 kilometers. And then the age, something like 2,500 years. So this is sort of an overall summary of the whole data set. And then for every island, we calculated what is the average sediment delivery rate per meter width per year. They're very small numbers and huge amount of variability. We lump them all together, we get this. We get an average sediment delivery rate of, on the order of 0.1 cubic meter per meter island width per year. Again, this number doesn't mean anything to you, but I can tell you, for example, you need at least 1 cubic meter per sediment per year to have a significant difference in terms of an island or a beach response to sea level rise. During the 2013 and 14 storms, on some of the beaches lost hundreds of cubic meters in a single winter season. So this is really a very, very small number that makes a difference. It builds islands over hundreds and thousands of years, but whether this is happening or not is not going to determine the fate of the islands. It's insignificant over the timescales that sea level is rising. I think that's a really important thing, because we can't rely on the natural sediment supply to keep the shorelines where they are. And it also gives us an indication if we want to make a difference in terms of island retreats, we need to be adding a lot more than this to these islands. If it is an adaptation strategy to add sand, we need to add at least 10 times more than that every year per meter. Okay, so the final bit, I really want to very briefly touch upon adaptation. I think we want to understand this process of overwash. We want to include island adjustment in any future modeling predictions of what these islands will look like in the future. And particularly, we want to model what the flooding regime will look like, because the flooding regime will determine whether island communities can live with that flooding regime, what they can do about it, or whether they just cannot live with that flooding regime. If the flooding regime is unmanageable, island communities have two options: building a massive seawall around the whole island, which is very expensive, and it's not going to happen on every atoll island because they're poor countries, and most of the islands have less than 1,000 people. It's just unaffordable to do that. The second alternative is relocation, which sometimes is talked about. Some islands in Fiji have been relocated already. And relocation is, I mean, if you imagine where you live, that you get told in 10 years' time, the whole village will move somewhere else. It's societally unacceptable, hugely traumatic. So there's almost like two options that I feel are quite unacceptable. One is too expensive, one is just, really cruel. And I believe that if we're looking at how these islands adjust as a result of rising sea level, we have this range of responses, mainly in this sort of red box, where there's lots of sediment. We can get from orange to yellow. If we have not a lot of sediment, quite energetic wave conditions and a rapid sea level rise, you might see quite an aggressive movement, but still, and we could drive the system too large, we could actually destroy the island altogether. Where we are on this really depends on a whole bunch of island factors like sediment supply, island size, whether the reef is growing or not, those sorts of things, and a whole bunch of ocean factors, which is the rate of sea level rise, the intensity of the storms, whether we're going to get a lot of overwashing or not. So depending on where you are, you have these sort of different scenarios of island adjustment. And I think we can work with these through various adaptation measures that I'm going to talk about in a minute. But we also do know that if you have an island that's got a seawall around it that is functional now and keeps the water out, rising sea level will at some point require increasing the coastal defences. And with the coastal defences, the island is not going to adjust. So it's almost like once you have a seawall, well, you basically signed up on that to do that in perpetuity almost. You can't go back from this to something like that. So I just want to very briefly talk about these adaptation measures. We recently completed a report for the World Bank. They liked some of our ideas, but they also liked some of our ideas not so much. But you've got protection, seawalls, breakwater, revetments, groins. You've got a new technique called island raising, which they've done in the Maldives and also start doing in the Pacific. It's basically building a new island or adding a lot of sediment on an existing island. Basically do the overwash process, but do it with bulldozers. And then you have the nature-based, I don't like the term nature-based solutions because they're not actually solve anything. They help the problem, but they're measures, vegetation, seagrass, mangrove restoration, artificial reef structures. These are all things that help things. They're no regret measures. No one's going to say, we should never have done that. We should never have restored that salt marsh or that seagrass patch. We should never have restored that mangrove. No one will ever say that. People would say, well, we should never have built the seawall. And then this is, to me, the really important one. I call it accommodation. It's basically allowing potentially island communities to deal with an island that is regularly flooded. I'm not talking about every week or every month, maybe not even every year, but every couple of years, there might be a flooding event that deposits maybe a couple of centimeters of sand on it. Whatever is on the island has to deal with that. So flood refuges, flood resilient housing, raising building plots. You build a new house, you raise it before you put the house on. Houses on stilt have to improve drainage. Land use changes, just the most vulnerable parts of the island. You take some of the important activities away, and you definitely need an early warning system. You got to make sure that people are safeguarded. If they have an island community that you say you should just accept the floods, you should at least warn them when it's happening. And then these really bad ones as well, relocation or migration to a different island, to a different country. And some of them provide protection to flooding, some to erosion, some increase flood resilience, and some strengthen ecosystem resilience. Now, the key point here is that different islands, different types of islands require different adaptation solutions. There's no one adaptation strategy that you can apply to all the islands. We've done a typology of islands in the Maldivian islands, and they range from really high protection like Male with a massive seawall around it, medium protection where most of it is natural, where we've got some massive breakwaters here, low protection where we have maybe only a harbor, something like that, to natural islands with nothing on it, and agricultural island with no defenses, and then we have resort islands and lagoons islands. Now, any adaptation strategy that might work on an agricultural island is not going to work on an island that's already protected with seawalls. So it's a bit like you're a DIY man or woman, and you do a job. Well, depending on the job, you pick the tool for the job. There's not one tool that you can do everything with. So very broadly speaking, if you have an island that's already very, very developed with seawalls, well, you have to stick to that particular adaptation set, because you can't just start planting mangroves and expect there to be a difference. And the ones that already have a significant amount of shoreline protected by coastal structures, well, you can't really take them away. You probably are on the path of ensuring that the whole island is protected. On the other hand, if you are an island that's completely unprotected, has no coastal protection structures, you should really start exploiting these other adaptation tools. And again, different, even within the types of tools, you pick tools that fit that type of island. And if you have an island that has a small amount of coastal protection, well, rather than extending that and embarking on full protection, maybe you should wind down some of that protection and go to use nature-based measures and accommodation. Now, the challenge really is to get people to buy into this and start playing around and trying these sorts of things out. And my job, I see, is to demonstrate the possibility of the efficacy of these measures using modeling. And then at some point, maybe there'll be some real action as well. So conclusions. You can sort of see them all pop up. Within limits, natural atoll islands are capable of keeping up with rising sea level through overwash-induced accretion. And you sort of see an example of a very long numerical simulation on the right. We started modeling this process using a process-based modeling framework. Once we've got that sort of sorted, we can then start to explore the efficiency of different adaptation strategies and apply them to specific islands. And I think, like I said, the challenge really is for atoll island communities to extend habitability despite being regularly flooded. The regular flooding is required for the islands to adjust, and the communities will have to try, or not will have to, may want to try and live with it, because I believe the other alternatives, seawall and relocation, is not actually an option for everyone. Now, so the answer to the question is no. It's not the inevitable outcome, and I hope everyone maybe agrees. This is a slide that a lot of people start off with. I finish with this because it stays on for longer. Doing science, doing research is great, and we always say we stand on the shoulders of giants. Well, don't have to be giants. We stand on the shoulder of our predecessors, which is great. We work on things that other people have worked on. It's also nice that I like to think that the next generation will use some of the work that we do, but the biggest pleasure is obviously work with other people. None of this research would have happened without a large group of people that I work with. These are international collaborators, technicians, academics, PhD students, and this is more or less the team of people that have been working on this current project called ARISE. And anyone interested in more, that's the QR code that gets you to the website. We like to think we keep it up to date every sort of 5-6 months. So there should be more stuff coming every 6 months. So thank you.
I need to find the microphone that thank you very much. Really interesting talk. I must admit, I was part of the
one of the no people.
At the very beginning to say that I thought it was inevitable. So that's really opened my eyes to some of the processes, the natural processes that are happening. What we're going to do now is agree to answer a series of questions. So we have a number of audiences. We have 2 audiences. We have you here, okay, and I'll give you the opportunity for those in the room to ask some questions in a minute. And then we have an audience that's online. So they obviously may have some questions as well. So we're going to switch between both audiences. But in addition to those, to make it completely inclusive, if there are people in the audience that want to ask a question, or those online as well who want to ask a question, but don't want to necessarily identify who they are, okay, then they're welcome as well. So we've set up a Mentimeter account, so there's a code there. So if you're dying to ask a question, but you don't really want to stick up your hand, okay, then feel free to pop your question into the Mentimeter. And my colleagues at the front here will read out those questions. Hopefully none of them particularly challenging, but read out those questions as well. As I am the host here, tradition usually has it that I'm allowed to have the first question.
Oh, right.
So yes, I have a question I'm going to start off with. You were talking about the migration of the island in response to sea level rise, the repurposing or remobilization of that sediment. And you pointed out that the actual elevation of the island changes and it migrates generally backwards.
Yeah.
I was trying to watch the models as they were happening. Does the actual gradient of the topography, so to speak, change? In addition to height, does it get steeper?
Yeah.
And what impact would that have, do you think?
There's a couple of really critical model parameters, and one is sediment size. The coarser the sediment size, the quicker the sediment settles. So you can actually build a ridge at the ocean side of the island and not do anything for the back of the island. You do the model with really fine sand, and most of the sand will go to the back of the island. So that's a really critical parameter, and I have to say our numerical model has not been properly calibrated for the different sediment sizes. It's actually a gravel beach sediment model, and for sand we'd have to, that's why we went into the lab to collect the data in the Delta Flume in the Netherlands. And the other thing that's really critical is the ability of the island to get the water to infiltrate. So if you have a very permeable, very porous island, the overwash will lose its power very quickly and will deposit the sand very quickly. Similarly, the roughness vegetation, for example, also plays a key role. If you have a very dense vegetation on the ocean side, it almost doesn't matter how big the overwashes is, everything gets dumped within the vegetation. So you're getting into some really complicated spatial varying factors that control the evolution of the island. But most of the islands have double ridge. A lot of them have a double ridge. One is an ocean ridge and then a lagoon ridge. One is a result of ocean overwash. The other one is a result of lagoon overwash. And often there's a swale in the middle where sometimes a mangrove swamp or sometimes it's just a swampy area. What that already tells you is that the center part of the island, it's quite difficult to enable that to build up, because even on a geological timescale, not many overwashes reach that part. And I think this is where the adaptation strategies come in, because you can maybe rezone the island in such a way that you develop different things in that area that doesn't get flooded. Or maybe that's where maybe you should artificially elevate it with bringing sand in from the lagoon. Or maybe that should remain your agricultural area and you should just not use it for anything else. So it's really complicated, because sediment size, permeability and roughness are all key, and they're spatially varying across the island, not only across the island, but also along the island and also between different islands. So this is where I would struggle a little bit. What I've showed you is just a generic simplified model, more than conceptual. It's a bit better than that, but it's very generalized and relatively simple. To go from that to real solutions for people, we need to almost like make it site specific to a certain island and get the right roughness and sediment size and all the right things in. And then we can start making some real reliable, robust predictions. At the moment, it's still like, okay, potentially this could work and this should work, but to make it work in the real world, it needs a lot more work.
Thank you. So I'm going to open up to the audience in the room. So does everyone in the room have a question? We're going to use the microphone so everybody can hear.
Thank you. When I think of an atoll, I think of coral surrounding a lagoon. I imagine that islands are very variable in their configuration. And I was wondering what proportion of islands would have a lagoon, and how these might be affected, the lagoons that is, might be affected by overwash.
Right.
From what you were saying just now, I got the impression that perhaps not.
No, okay.
Very much just getting an area of swamp in the middle. But I suppose some lagoons might be quite important to life on the island. I'm thinking of human life on the island, as harbors and that sort of thing.
I think you're talking about lagoon islands within the lagoon. They tend to be made out of sand. They tend to be a lot lower than on the ocean side. I think it's important to realize that the elevation of the island is controlled by the wave and water level conditions that were experienced during its formation. So the more energetic the wave conditions, the higher the island. So the lagoon islands will only experience waves generated in the lagoon. So these be wind waves, probably less than 2 meters most of the time. There'll be very short waves as well. They will have less run up. So these islands are going to be a lot lower than the ones on the ocean side, on the rim. And they will also experience waves coming from all sorts of directions, depending on where they are situated in the lagoon. If they're in the middle of the lagoon, they get waves from all sorts of directions. So they won't form a nice linear feature with maybe some ridges and a swale in the middle. They tend to be more circular, less with an area in the middle. But they do overwash. They also tend to be a lot smaller. But in essence, the behavior would be the same. I mean, less energetic waves will wash sand on top of the lagoon islands. It will also raise the elevation of it. So it's just even less dramatic overwash events on those lagoon islands. But most people live on rim islands. I mean, the lagoon islands in the Maldives are resort islands. And most resorts have houses on stilts and They also have lots of coastal protection works already around it. The new islands that are generated in the Maldives, the new resort islands, invariably they're lagoon islands, and they have really weird shapes that are totally out of sync with the wave conditions. So they immediately need lots of coastal defenses. So I leave them out, but the natural lagoon islands will do exactly the same as what I've described, but they'll have a less dominant wave direction. They will not contain gravel, and they will be a lot lower.
Thank you.
Okay, we're going to move online now. So,
Sure, I have a couple of questions actually from Alistair Curry online. First one is, does the sea level rise input in the numerical modelling account for hydroisostatic changes as well as other sea level rise components?
No, we just feed in I guess a predicted sea level rise of, I think, 3 or 4 millimeters per year, and we run that over 100 years. So no.
Okay, nice and simple.
But that can be done. I mean, it's just about a different boundary condition. At the moment, we're just looking at a constant sea level rise due to, constant one.
Thank you. Hopefully that answered Alice's question. His second question is, if waves attack from all directions across the seasons, will island retreat narrowing not eventually consume small islands irrespective of sediment accretion?
If waves come from different directions?
From all of the different directions.
Yeah.
Will island retreat not eventually?
Oh, yeah, okay. Yeah, well, we'll go back to the lagoon islands, where I guess a lagoon island that's like a flat pancake that will get waves from all sorts of directions at the same time as a rising sea level will basically, from a pancake, it will become a donut. It'll just shrink from all sides, but it will still increase in height. So yes, but like I said, the rim islands have mainly waves coming from one direction, mainly the ocean side or the lagoon side, and at both sides the waves will approach what we call shore parallel. So because of the reef platform on which the island sits, even if the waves in the ocean arrive under an angle, by the time they hit the reef and they go and hit the island, they will be parallel. So you get, rim islands tend to be elongated, and like I said, with a ridge on either side and a swell in the middle. But yeah, lagoon islands will slowly become narrower and narrower and higher, and they may just at some point just disappear. I mean, really small islands will be lost first because there's only a small amount of sediment there, and they'll be the ones that disappear first. A very wide island, you can imagine, can retreat by quite a lot before there's no space to live anymore. So island size is important.
Okay, thank you. Back to the room.
thank you. So,
Malcolm.
Sorry, voice going. I voted that yes, they'd be drowned.
Yeah, bad.
And
Expected
when
more.
you finished your lovely
Yeah.
presentation, I really enjoyed the modelling and everything else, but I would have still voted yes.
Yeah.
And the reason for that is that I have 5 very big elephants in the room. I'm not going to go through them all, otherwise I'll be thrown out of here. I mean, let's be honest. The sea level rise predictions, and the reason why I'm interested in this is that I designed the Thames Barrier a few years back, 1971, and I've always been sitting there wondering if it's going to get flooded, and it will. But those sea level rise calculations are all based on Newland tide gauges and everything else. And it's historical, really is historical. But what we're looking at now, and I looked it up today, carbon dioxide in the atmosphere is 425 parts per million as of 9 o'clock this morning. Now, we know the hockey stick curve is going up at a phenomenal rate.
Yeah.
But if I look back to the Pliocene and the Miocene, I can see what that carbon dioxide level was. I can see what sea level was. And even if you just go back into the middle to late Pliocene, sea level with about the same carbon dioxide content in the atmosphere as today was 25 meters higher. Now, the problem I think we have, and nobody, it's the elephant in the room. the CO2 graph is going up so rapidly that sea level rise, ice melt and everything else is lagging behind, and we don't know when it's going to catch up.
Yeah.
That's the first big problem I have, and I've got all the data back through the research I've done on the late tertiaries. My other elephants, which weren't mentioned, marine heat waves, which cause massive bleaching. We had 3 marine heat waves around the UK last year. That's going to have a dramatic effect as we move forward in time. Ocean acidification, yes, it's always on the back burner that it's going to cause something. But when you look at all this information and then apply it to some geological examples where in the past we've seen reef drowning events, we can actually plot them very accurately. I mean, I'm thinking of one in particular in Saudi Arabia. Well, if Saudi Arabia is going to exist shortly, you know, in the Middle East, there are countless examples of reefs being drowned. In Portugal, there's Rudis reefs being drowned, and the events really geologically are very rapid. So I have these big elephants in the room.
I count 4, but can I respond briefly to all of them?
No.
Yeah, no, I'd like to, because the first and the fourth, I probably should have qualified the question. I probably should have said who thinks the inevitable drowning over the next century, maybe, or 2 centuries. So you say geologically very fast, rapid changes. That was your first point and your fourth point. Were you talking about drowning happening of coral reefs because of 5-10 meter sea level rise in hundreds of years? Or are we talking about thousands of years? So I think on a geological timescale, yeah, it's probably inevitable that at some point they will drown. I'm more looking at the non-geological timescale. I'm looking at the timescale where people make decisions about what to do with these atoll islands now. And I see World Bank, Japanese Development Bank, Asian Development Bank trying to pour massive amounts of money into these small island developing states to build seawalls.
I'm not talking about geological timescales.
Right.
What I'm saying is that the present situation with carbon dioxide, marine heat waves, and everything else is going to happen between now and 2100.
Okay.
I am not talking geological.
Okay. So point 2 and 3, which was the heating and the acidity. If the reef is dead, that's not going to necessarily affect the island as such. It affects tourism, but in fact, it will produce an influx of sediment for a short period of time, and then it will stop. But I think I've demonstrated that the amount of sediment produced by the reef system at the moment, average, is really not making much of a difference. So whether the reef is dead or alive, it's awful if you're into ecology and nature conservation, but for the island itself, it's not going to make much of a difference. I think a much bigger issue for these island communities is that the tourism will just drop dead as soon as the reef dies. But for the islands themselves, I don't think it makes much of a difference. So that, I think I've replied to the 4 elephants briefly. I get your point about the geological timescale, but I'm talking about next 50 to 100 years.
The important thing is, if you go to Tor Bay and you look at the raised beach on Hope's Nose, it's 7.2 meters above present sea level.
Yeah.
And it was there with carbon dioxide levels.
Sure, we'll go to that point in the future. Sure.
Parts per thousand, not
okay.
425.
Yeah.
Okay, conscious we've still got other questions online as well, so to move on to that.
Yeah, just one. You talked about in the modelling the amount of sediments and how that can vary the rates and also the wave dynamics and storm surges and so on. Does the type of sediment that the island's made of have any impact? Protection.
Yeah. There's gravel islands. You find them on the more exposed parts of the rims, and sand is the more sheltered parts of the rim. Gravel tends to form very steep and high ridges, almost like a natural defense, almost like a natural seawall sometimes. whereas sand tends to be made much lower ridges, and sand gets washed much further down to the back of the island. So gravel islands are much higher generally than sandy ridges. Similarly, bigger wave conditions also form higher islands than lower wave conditions. So sediment size is important, yes.
How about the composition of the sediment, not just the size of the sediment?
What do you mean with composition, though?
The type, what type of mineral or rock type?
It's all carbonate. It's all carbonate, all the same density. Yeah.
Good. Thank you very much. That's any further questions from the room? No? Did anything come in through the Mentimeter or no? Okay.
Anyone who does.
Oh, the ones you asked him to mention. Okay. So in which case, I'd like to once again thank Kurt for launching this series and his talk today. We do have a series of questions. So those that attended both in person but also online. Okay. We have a series of questions that the same questions we're going to pose at each of the talks that we do. So if you get the opportunity, please. Just to say that and